Hey guys. Yep, good afternoon. So let me remind you that there's an exam tomorrow. Okay. Okay. So it starts at noon and ends at midnight. If whatever happens and you're having technical difficulties or something like that, please try to email me sooner rather than later. I know that can happen. How many questions? Let me see. Mint. Four questions, all worth the same. Some might be easy. Some might be similar to like some of the practice questions on the assignments 1, 2, and 3. And there might be a more challenging question. But all in all, I hope that you can kind of I think you can remember that on top of that, you also have to scan your solutions and upload them and then all that stuff. So give yourself at least an hour plus more time to do all that uploading stuff. Yep. Okay. Oh, and because I think someone asked something like that, there's no window, it's just the entire 12 hours is the time. It's just like, I think that a 2-hour window should be from taking the whole 12 hours. I wouldn't really suggest that though, but it's up to you. Okay. Any other questions? Okay. If you do have a question come up that you think of, you can just interrupt. We'll get back to it, But for now, I guess it means that we just this is one of the, to me, I think of this as being one of the big theorems of this course. Okay. So let me remind you, this is the Cantor-Schröder-Bernstein theorem. Okay. Okay, what does it say? It says, suppose the size of the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then they actually have the same cardinality, right? And for this to make any sense, we need to remember what these symbols mean, and this is for sets A and B, right? And what are these symbols? Well, this means that there exists a one-to-one function f going from A to B, and also g going from B to A. G is one-to-one. That's what our hypothesis says. And then the conclusion says that there exists one-to-one and onto H from A to B. Okay, because that is what we have said is what it means for two sets to have the same size when there's a one-to-one and onto function between them. In other words, we match up every element of A with an element of B and vice versa, right? and just to remind you, this is kind of like how, this is a solution to the problem of like, before we worked with numbers and everything, we needed a way so that, if you had 5 sheep and maybe I have, I don't know, 5 goats and we want to trade them. No, maybe goats is bad. What would you want to trade a sheep for? Anyways, here's the sheep. Here's my sheep. There's my sheep. And then on the other hand, maybe there's like 5 canoes or something, or boats. Here's my 5 boats. And we want to be fair, so we match up each one. We match them up. In other words, I have a 1-to-1 and onto function going from all the sheep to all the boats. Okay. Now I know no one is being cheated, well, because we've paired them all up. We have the same number. Okay. And so we just use that notion and extend it to arbitrary sets, and is what we get. Okay. And now there's this problem. We want cardinality to satisfy this property of anti-symmetry. We've shown that if m is less than or equal to n and n is less than or equal to m, then m equals n, but we want that to be true for the cardinality of sets. And this is very much non-trivial. That's why it's like a theorem. Okay. And last class, we proved that this theorem would follow from a lemma, which I will write down now. Okay. What is the lemma? So let me just remind you, proof, which we just discussed on. Well, that's not good, but it follows from the following. That's awkward. Lemma. So we have sets A1 contained in B contained in A, and suppose the cardinality of A1 equals the cardinality of A. Good. Okay, so let's set up things, proof, and then we will draw a picture. Okay, so by hypothesis, we have f from A1 to A is 1-to-1 and onto, and A1 is contained 1-to-1 and onto function from B to A. And let me, and for my suppose, let me go from A to A1 instead of from A1 to A. Okay. Oh yeah. Before I continue with this lemma, let me tell you an example of the kind of thing I mean. Okay, before I continue. Okay. Example, maybe A might be the integers, and A1 might be the natural numbers. No, maybe it's like maybe A1 is the odd numbers, the odd integers. Like that. Okay, and B, no, let's call that B. And let's call A1 kind of the numbers like this. Okay. So actually there's a one-to-one and onto function from A to A1. And that is to take an integer n and map it to 4n minus 1. This is one-to-one onto from A to A1. And this set of integers have the same size. Okay. And as a corollary to this theorem, well, that tells us that anything containing this set and cardinality. Okay, so Cantor-Schröder-Bernstein theorem would tell to the number of elements of set. Okay. And I actually want to tell you another example. A might be the real numbers. A1, so I'm going to use the exponential set of real numbers, which are positive. And we have f from R to A1. This is one-to-one and onto A1. It's onto A1. Bernstein theorem will tell us that, or well, this lemma will tell us that if you have any set that contains A1, for example, if you take B to be all the real numbers, there exists G from A to B, which is one-to-one and onto. Okay. Okay. So that is what we're trying to do. It is, notice that it seems kind of hard to make up a nice function going far. The reason why it might be hard is I'm just going to say like from real analysis reasons. This is like, yeah, anyways, okay. Okay, so now let's just try and prove our lemma. Sure. Here's A. And living inside that is B. And living inside that is A1. Okay, and we want to construct a one-to-one and onto map from B to A. Okay. Okay. And we've kind of like part of our job is done because we've got a mapping from some part of B, this part, to A, all this stuff. Okay. So if B equals A1, we're fine, but there's like this problem of this gap. Okay, so let me shade in this. This is our problem area. Okay. But what we can do is we can try and make our problem area smaller. 1 equals f of B. Now f of A is A1, so f of B is going to be contained in A1. So let's call that B1. Okay. Okay. And now let's map, let's make A1 smaller too. Let's put A2 to be f of A1. Now, B1 is contained in A1. So, sorry, so A1 is contained in B. So f of A1 is going to be contained in f of B. So that means just A2 is contained in B1. Here we have A2. This smallest circle so far. Okay. Now A2 has the same cardinality as A. Okay. So okay. So anyways, right. Kind of, let's just keep on making our problems smaller and smaller and see what happens. Okay, so then we do B2 is just f of B1. A3 is f of A2. We get this concentric thing happening. And on and on. Okay, and now we have to figure out a way. Okay, and notice what happens. So in general, we have an or an plus 1 is f of an, and bn plus 1 is f of bn, and we have a contained in b, contained in a1, contained in b1, which contains a3, and on and on. And each a has the same size as each ai has the same cardinality as a. Okay, and we want to construct a. And the problem is this shaded area. Okay, and here we kind of have a trick. And the trick is the following. Take this shaded area and just put it in, just map it one-to-one and onto to the next shaded area. And then take that shaded area and move it on to the next shaded area, like that, and keep on doing that. Okay, so that is our plan. And leave everything that's not in a shaded area, just leave it. Okay. So let me summarize the plan. Okay. So the plan, we define a0 equals a, and an plus 1 equals f of an for n greater than or equal to 0, b0 equals b, bn plus 1 equals f of bn for n greater than or equal to 0. Then we have a contains b, contains a1, contains b1, contains a2, and on and on. And we want to give a special name to the shaded area. The first shaded area is b, the set difference of b minus a1. We'll call that c1 equals b0 minus a1. Maybe I'll call that c0. So we'll also define our shaded areas. We'll define c1 equals b1 minus a2. Define c2 equals b2 minus a3, and on and on. Good. And what the trick is just that f of c0 equals c1. With this definition, we have this property. F of c1 equals c2. And f of cn equals cn plus 1. That's our trick. Okay, let's prove that the trick works. So, proof of the trick. Okay, so Cn equals all the x's in Bn such that x is not in An plus 1. Okay. Then let x be in Cn. Then f of x, well, x is in Bn. Bn plus 1 is just, the definition of Bn plus 1 is just f of Bn. So f of x is in Bn plus 1. X is in An plus 2. Then x is in An plus 1. Why? Because An plus 2 is just f of An plus 1. And f is 1 to 1 and on to and everything, right? Meaning that if f of x is in An plus 2, well, that just means that x was in An plus 1. Okay. That would mean that x was not in Cn. Okay. So x is not in An plus 1. So f of x is not in An plus 2. In other words, so f of x is in Cn plus 1. And then you also have to show that, well, if f of x is in Cn plus 1, then x is in Cn. So suppose f of x is in Bn plus 1, but f of x is not in An plus 2, i.e., in other words, f of x is in Cn plus 1. Well, if f of x is in Bn plus 1, that just means x is in Bn. And if f of x is not in An plus 2, that just means x is not in An plus 1. So that just means x is in Cn. Okay. Okay. So now we have our function f maps C0 to C1, it maps C1 to C2, maps C2 to C3, and each time you do that, it's 1 to 1 and on to. Okay, so I just want to go back to the picture I was drawing, and then we'll take a break, and then after the break, we'll finish off this theorem. So here's a picture I was drawing. Wait for it, there it is. Okay, here's C0. The C's are all the shaded areas. Okay, and I've shown that my function f is 1 to 1 onto and takes C0 to takes C2 to C3. Okay, so this is kind of like, I like to think of it as like kind of like procrastination. My bubble is A1 and you kind of know what to do with it. You don't know what to do with the shaded area that lies between B and A1. So you just you kind of put it off, you put it into this smaller shaded area. And then that's fine, but now you do this even smaller shaded area. And you just keep on doing that over and over again. So each successive smaller shaded area, you move it into the next smallest one. Okay. And then what do you do with this these non-shaded areas? Well, you don't do anything, you just leave it alone. Okay, and then what you actually see is that you get a 1 to 1 and onto function from B to A1. Okay, and we shift the shaded alone. Okay. And so we've kind of like, yeah, we keep on moving the problem. We keep on putting it off, but it actually works out. Okay, so it doesn't normally work in real life, but here it works. Okay, so let's just take like let's take a break until 3:45. And then we'll try and wrap up the proof of this theorem. Okay, so just hold on until 3:45. Yep. Okay.